Steam locomotives didn't vanish because they failed. They vanished because railroads stopped waiting for them. So why were machines that still worked pushed aside almost overnight? The answer didn't come from breakdowns or accidents. It came from numbers railroads could no longer ignore. To understand why steam was replaced, you first have to understand why it dominated railways for so long. Steam locomotives did not rule the world because they were efficient or easy to operate. They ruled because, at the time, they were the only machines capable of solving a very specific problem. Railroads needed massive pulling power using materials and technology that already existed. They needed something that could be built, repaired, and operated without complex supply chains or advanced infrastructure. Steam delivered exactly that. If steam was inefficient and dangerous by modern standards, why did it work so well at first? Because steam matched the world it was born into. Coal and water were cheap, abundant, and available almost everywhere railroads expanded. Steam locomotives were self-contained systems that did not rely on external fuel networks or electrical grids. They could be built with existing industrial knowledge and maintained by crews trained through experience rather than formal engineering education. In an era still learning how to coordinate large systems, steam fit perfectly. Steam locomotives were not just machines. They were moving power plants. At their core, steam locomotives are brutally simple. Coal is burned to heat water. Water becomes steam. Steam expands, pushing pistons that turn wheels. There are no computers, no sensors, no electronics, just pressure, steel, and motion. That simplicity created incredible power, but it also created constant demand. But here's what no one talks about. What it took just to keep one of these things alive. Constant attention and constant fuel. Steam engines burned coal even when standing still to maintain pressure. Firemen shoveled fuel continuously. Engineers monitored water levels, pressure gauges, and mechanical balance at all times. Steam never rested, and neither did the crews operating it. Running a steam locomotive was not automation, it was controlled labor. This shaped the entire railroad ecosystem. Routes were planned around water stops. Entire towns existed only to supply coal and water. Rail yards were filled with coaling towers, water cranes, ash pits, and service sheds. Steam did not just move trains, it dictated geography, labor, and logistics. Well, how expensive was this system behind the scenes? Extremely expensive. Railroads had to maintain water towers every few dozen miles, stock coal across the network, and employ large servicing crews. Steam locomotives required frequent inspections, constant lubrication, and long maintenance cycles. After heavy runs, engines often spent days or weeks in workshops instead of hauling freight. Railroads accepted this cost because there was no alternative. For decades, steam was not the best option. It was the only option. But as rail networks expanded, steam's weaknesses began to multiply instead of scale. Trains grew heavier, routes grew longer, schedules grew tighter. Steam could pull almost anything, but it demanded enormous resources to do it. Was steam actually efficient at turning fuel into movement? Because most of the energy never touched the wheels at all. It escaped as heat, smoke, and steam. A steam engine could burn tons of coal per hour simply to maintain pressure, even when not operating at full speed. Efficiency was sacrificed for brute force. Steam solved one problem by creating many others. Then there was danger. Quick pause here. If you're enjoying this breakdown and want more stories about how technology quietly reshaped history, let us know in the comments which era you find most fascinating: steam, diesel, or electric. And if you haven't already, consider subscribing. These are exactly the kinds of stories we explore here. Now back to the bigger picture. How risky was steam railroading for the people running it? Very risky. Boiler explosions were a constant threat, especially in early railroading. Poor maintenance, bad water quality, or excessive pressure could turn a locomotive into a bomb. Even without explosions, crews endured extreme heat, smoke inhalation, soot exposure, and intense physical labor on every run. Running steam was not just a job, it was endurance under pressure. Maintenance was another hidden cost. Boilers had to be cleaned regularly. Tubes required inspection. Bearings needed constant lubrication. After long runs, steam locomotives often spent more time in workshops than on the main line. Railroads tolerated this because steam had built everything they depended on. So what finally pushed railroads to question steam? Scale and economics. As rail systems expanded, steam's inefficiencies became impossible to ignore. Longer routes meant more stops. Heavier trains meant more fuel. Urban growth increased pressure to reduce smoke and pollution. Operating costs began rising faster than revenue. Steam was no longer just inefficient. It was holding railroads back. By the early 20th century, steam had reached its peak. Engineers refined it relentlessly. Higher boiler pressures, larger engines, more complex valve systems. But every improvement added weight, cost, and maintenance without fixing the core problem. If steam kept improving, why did it still fail? Because steam was fighting physics itself. Heat loss, material limits, and mechanical complexity imposed ceilings that no refinement could overcome. Bigger engines required bigger crews. Higher pressures increased risk. Efficiency gains were marginal compared to rising operational costs. Steam could pull the world forward, but it demanded everything in return. Quietly, railroads began asking a dangerous question. Not, how do we improve steam? But, how long can we afford this? If steam had built the modern railroad, what could possibly replace it? The answer would not come from fire and water. It would come from oil, engines, and a completely different way of thinking about power. When diesel locomotives first appeared, railroads did not rush to embrace them. In fact, many railroad executives openly doubted they would ever replace steam. To the people running rail networks, diesel looked smaller, quieter, and far less dramatic than the massive steam engines they trusted. Steam has proven itself over decades. Diesel, by comparison, felt experimental. If steam was expensive and inefficient, why didn't railroads jump at the chance to replace it? Because steam was familiar. Railroads had already invested enormous amounts of money into steam infrastructure, maintenance facilities, spare parts, and skilled labor. Entire operating systems were built around steam. Switching to diesel was not just a technical decision. It meant writing off decades of capital and retraining an entire workforce. Diesel wasn't just a new locomotive. It threatened an entire way of working. Early diesel locomotives also didn't inspire confidence. They were underpowered compared to large steam engines. They struggled with heavy freight. Breakdowns were common in the early years. Spare parts were expensive. Skilled technicians were rare. To many railroad managers, diesel looked like a niche machine for shunting yards and short passenger routes, not a replacement for mainline steam power. So what changed their minds? Railroads began running the numbers. When diesel locomotives were tested side by side with steam, the difference in operating costs became impossible to ignore. Diesel engines consumed fuel only when power was needed. Steam engines burned fuel constantly. Over time, fuel savings alone began to outweigh diesel's higher upfront cost. Diesel didn't win with spectacle. It won with spreadsheets. One of diesel's biggest advantages was something steam could never offer: predictability. Steam locomotives varied wildly in performance depending on crew skill, fuel quality, water quality, and maintenance condition. Two identical steam engines could behave very differently on the same route. Diesel engines, by contrast, behaved almost identically every time. Why did predictability matter so much? Because railroads run on schedules and margins. Predictable performance made it easier to plan timetables, allocate crews, and manage fuel costs. Trains arrived on time more often. Breakdowns became less frequent. Maintenance could be scheduled instead of reactive. Reliability mattered more than raw power. Then came one design decision that changed everything: diesel-electric propulsion. Instead of mechanically driving the wheels, diesel engines powered generators. Those generators produced electricity that fed traction motors mounted on the axles. Why was this such a big deal? Because it eliminated complex mechanical transmissions. Power delivery became smoother and easier to control. Traction motors delivered high torque at low speeds, making diesels ideal for heavy freight. mechanical failures dropped sharply, and engineers gained precise control over acceleration. Diesel locomotives didn't fight physics. They worked with it. This design unlocked another critical advantage: multiple unit control. How did this change railroad operations? Multiple diesel locomotives could be coupled together and controlled from a single cab. If more power was needed, railroads simply added another unit. If one unit failed, it could be isolated without stopping the train. Steam locomotives, by contrast, required additional crews and complex coordination when double-heading. Power became modular, flexible, scalable. Crew requirements also dropped. Diesel locomotives did not need firemen. They did not require constant monitoring of boilers or water levels. Starting a diesel took minutes instead of hours. Shutting it down was simple. What did this mean for labor costs? They dropped significantly. Smaller crews, shorter preparation times, and reduced physical strain lowered operating expenses. Over long distances and large networks, these savings compounded rapidly. Steam demanded manpower. Diesel demanded management. Maintenance was the final blow. Steam locomotives required frequent servicing. Boilers needed cleaning. Tubes required inspection. Bearings demanded constant lubrication. After major runs, engines often sat idle for days. Diesel locomotives stayed on the rails. How big was the maintenance difference? Dramatic. Diesel engines require regular servicing, but far less frequently than steam. There were no boilers, no ash disposal, and far fewer exposed moving parts. Locomotives spent more time hauling freight and less time in workshops. For railroads, this changed everything. Once these advantages became clear, the transition accelerated. Steam fleets were retired at astonishing speed. Entire classes of locomotives were scrapped within a few years. Rail yards that once serviced steam engines were redesigned for diesel maintenance. Why did steam disappear so fast once the shift began? Because diesel exposed how fragile steam economics had become. Once railroads experienced lower costs, higher reliability, and simpler operations, there was no reason to go back. Steam could not compete on efficiency, labor, or scalability. The age of steam did not end with a dramatic failure. It ended because something better arrived. But diesel was not perfect. It still burned fuel. It still produced emissions. And it still carried its energy on board. If diesel solved so many problems, why wasn't it the final answer? Because efficiency has limits. And the next solution would not improve the engine at all. It would remove it. By the mid-20th century, diesel locomotives had clearly won. Steam yards were dismantled. Boilers were scrapped. Entire generations of railroad workers watched the machines they had mastered disappear. For railroads, diesel felt like the final answer. If diesel solved steam's biggest problems, why did railroads keep searching for something else? Because diesel solved operational inefficiency, but it did not eliminate dependency. Every diesel locomotive still carried its own fuel, burned it on board, and paid the price in emissions, mechanical wear, and rising fuel costs. As rail traffic increased, those limits became harder to ignore. Diesel fixed the engine problem. It did not fix the system problem. As cities expanded and rail corridors became denser, diesel locomotives began running into new challenges. Urban pollution became impossible to hide. Noise complaints increased. Fuel costs fluctuated wildly with global markets. And perhaps most importantly, speed became the next frontier. Why did speed suddenly matter so much? Because railroads were no longer competing only with themselves. They were competing with cars, trucks, and airplanes. Passenger rail needed faster acceleration. Freight rail needed higher throughput. Diesel engines, while reliable, had physical limits on how quickly and efficiently they could deliver power. Efficiency stopped being about cost alone. It became about performance. Rail engineers began asking a different question. Not, how do we improve diesel? But, what if the locomotive didn't have to generate power at all? And that question led to a radical idea. Here's the twist. The next major leap in railroading did not come from a better engine. It came from removing the engine entirely. What happens when a locomotive no longer carries its own power source? Electric locomotives draw power from external infrastructure through overhead wires or third rails. Instead of burning fuel on board, they receive electricity generated elsewhere and deliver it directly to traction motors. This eliminates combustion, exhaust systems, and many mechanical losses at once. The locomotive stopped being a power plant. It became a receiver. This change transformed everything about performance. Electric motors deliver maximum torque instantly. There is no warm-up time, no lag, no delay between command and movement. Why is instant torque such a big deal for trains? Because trains are heavy. Electric traction allows faster acceleration, smoother control, and stronger performance on steep gradients. This is especially important on busy corridors where trains must start, stop, and merge frequently without losing momentum. Electric trains don't fight gravity. They overpower it efficiently. Maintenance differences became impossible to ignore. Diesel engines have pistons, fuel injectors, exhaust systems, and lubrication networks. Electric locomotives have far fewer moving parts. How much did this change maintenance demands? Dramatically. Fewer moving parts meant less wear. Less wear meant fewer failures. Electric locomotives spent more time running and less time in workshops. Over decades, this translated into significantly lower lifetime costs. Reliability moved from the engine room to the power grid. But electric railways came with a catch. A big one. If electric locomotives are so efficient, why didn't they replace diesel everywhere? Because electrification is expensive and inflexible. Building overhead wires, substations, and power distribution networks requires massive upfront investment. It only makes sense where traffic density is high and usage is constant. Vast rural networks and low-volume freight routes cannot justify the cost. Electric trains thrive where infrastructure exists. Diesel survives where flexibility matters. This is why modern rail systems look the way they do today. Electric dominates high-speed passenger lines, dense freight corridors, and urban transit systems. Diesel continues operating on long-distance freight routes, remote regions, and flexible networks. So did diesel actually fail? No. Diesel did exactly what it was meant to do. It replaced steam, stabilized rail operations, and made modern rail networks possible. But like steam before it, diesel eventually encountered limits it could not escape. Every solution creates the conditions for its own replacement. Railroad history is not about better machines replacing worse ones. It is about answers replacing questions that no longer fit the world. And that brings us to the final question. By the time electric traction entered serious discussion, railroads were no longer thinking the way they once had. Steam had taught them brute force. Diesel had taught them efficiency. Now, the challenge was scale. Railways were no longer just moving trains. They were managing entire transportation ecosystems. What actually changed when railroads stopped focusing on locomotives alone? They realized that the biggest gains no longer came from improving individual machines. They came from optimizing the system around them. Scheduling, energy distribution, traffic density, maintenance cycles, and network coordination began to matter more than raw horsepower. The locomotive stopped being the star. The network became the story. This is where the comparison between steam, diesel, and electric becomes impossible to ignore. Steam locomotives were powerful but isolated. Each engine operated as its own world, demanding fuel, water, labor, and constant attention. Diesel locomotives introduced efficiency and autonomy. They reduced labor, stabilized costs, and made long-distance operations predictable. Electric locomotives went one step further. They removed the engine entirely and tied performance directly to infrastructure. Why did this shift matter so much for modern railroads? Because modern rail systems are about throughput. How many trains can move through a corridor? How quickly can they accelerate? How little downtime interrupts operations? Electric traction excels at this because it delivers consistent power without adding weight, fuel, or mechanical complexity to the train itself. Efficiency stopped being local. It became systemic. This explains why electrification spread unevenly. Busy passenger corridors adopted electric first. High-speed rail demanded instant acceleration and sustained speed. Urban transit systems needed clean, quiet operation. Freight rail, however, remained mixed. Why didn't freight rail switch completely to electric? Because freight routes are long, variable, and often remote. Electrifying thousands of miles of low-density track is not economically viable. Diesel remains more flexible for these environments, even if it is less efficient at peak performance. Railroads chose balance over perfection. This hybrid reality reveals something important. No locomotive type truly won. Each one solved the problem of its time. Steam built the network. Diesel stabilized it. Electric optimized it where conditions allowed. So what ultimately determines which technology survives? Context, geography, traffic density, energy availability, and economics determine which system makes sense. Technology does not replace itself in a vacuum. It responds to pressure. Progress isn't about better ideas, it's about necessary ones. What railroads learned through this transition was something deeper than engineering. They learned that dominance is temporary. Steam ruled until its costs became unbearable. Diesel ruled until its limits became visible. Electric now rules where infrastructure supports it. Does that mean electric will eventually be replaced too? History suggests yes. Electric traction is only as clean and efficient as the energy feeding it. If electricity comes from fossil fuels, emissions are shifted rather than eliminated. Future change will depend less on locomotives themselves and more on how energy is generated, stored, and distributed. The next revolution may not be mechanical at all. Railroads no longer ask, "What engine do we need?" They ask, "What system makes sense here?" That shift is the real legacy of steam's replacement. By the time diesel locomotives began spreading across main lines, something subtle had already happened. Steam hadn't been defeated in a dramatic way. It had simply become inconvenient. Railroads were no longer fighting to move trains at all. They were fighting to move them predictably, cheaply, and without interruption. And steam struggled with all three. If steam was still powerful, why did railroads start losing patience with it? Because steam demanded constant attention even when nothing was wrong. A steam locomotive burned fuel just to stay ready. It needed crews hours before departure. It required inspection after nearly every major run. The cost was not just coal, but time, labor, and lost scheduling flexibility. Steam railroads didn't just operate trains. They managed exhaustion. Diesel exposed this weakness brutally. A diesel locomotive could sit idle without wasting fuel. It could be started in minutes. It didn't require water stops. It didn't care if the route passed through deserts, frozen plains, or remote regions with no infrastructure. That freedom changed how railroads thought. How did this shift affect entire rail networks, not just locomotives? It simplified everything. Routes no longer needed to be planned around water and coal access. Maintenance schedules became centralized instead of scattered. Railroads could consolidate facilities and cut operating staff without reducing capacity. The network stopped serving the locomotive. The locomotive began serving the network. That reversal mattered more than horsepower. Steam also struggled with standardization. No two steam locomotives were truly identical. Designs varied by region, builder, and purpose. Each required specialized knowledge and parts. Diesel changed that. Why did standardization accelerate steam's downfall? Because diesel locomotives could be mass-produced, standardized, and swapped easily. Crews could move between units with minimal retraining. Parts inventories shrank. Repairs became faster and more predictable. Railroads stopped relying on craftsmanship. They started relying on systems. Steam was an art. Diesel was logistics. As costs dropped and reliability increased, the decision stopped being philosophical. It became mathematical. Steam was no longer just old-fashioned. It was expensive. And once railroads realized that, the transition accelerated with shocking speed. How fast did steam actually disappear once the balance tipped? In some countries, entire steam fleets were retired within a decade. Locomotives that had defined railways for generations were scrapped, sold, or preserved as museum pieces almost overnight. The change felt sudden because the decision had already been made years earlier. Steam didn't fade away, it was switched off. But even diesel's dominance carried the seeds of its own limitation, because efficiency solved one problem and exposed another. By the mid-20th century, diesel locomotives had won decisively. Steam was gone from the main lines. Workshops were redesigned. Crews were retrained. Railroads finally had a machine that matched the scale of their ambition. But winning a battle does not mean winning forever. If diesel solved steam's biggest problems, what was still holding railways back? Fuel. Diesel locomotives still carried their energy on board, burned it continuously, and paid the price in heat, emissions, and mechanical wear. As trains grew heavier and schedules tighter, fuel consumption became a limiting factor rather than a solved problem. Diesel freed railroads from steam. It did not free them from fuel. Another issue began to surface quietly: speed. Diesel locomotives were excellent at hauling freight across vast distances, but as passenger expectations changed, railways needed faster acceleration, higher sustained speeds, and smoother operation through dense urban corridors. Diesel could do it, but not efficiently. Why did speed expose diesel's limits? Because diesel engines perform best within specific operating ranges. Pushing them harder increases wear, fuel consumption, and maintenance costs. At high speeds, mechanical losses grow rapidly. The faster trains went, the more diesel began to resemble steam in one familiar way: wasted energy. Efficiency had won once. Now it was being tested again. Cities added another layer of pressure. Smoke that was acceptable on rural freight lines became unacceptable in tunnels and terminals. Noise complaints increased. Air quality regulations tightened. What diesel gained in autonomy, it lost in environmental tolerance. Railways needed something cleaner, quieter, more scalable. What kind of locomotive could increase performance without increasing pollution? One that did not generate power on board at all. Instead of carrying fuel, it would draw energy from an external source, allowing power generation to be optimized elsewhere. This idea wasn't new, but now the conditions finally favored it. Diesel had done its job. It had exposed what the next answer needed to be. Electrification had existed in pockets for decades, mostly in urban rail and mountain routes. But now, railways began looking at it not as a niche solution, but as a systemic one. And once again, the transition did not begin with excitement. It began with spreadsheets. Why did railroads hesitate, even knowing electric trains were more efficient? Because electrification is not just a locomotive choice. It is an infrastructure commitment. Overhead wires, substations, power distribution, and long-term planning require enormous upfront investment. Railroads needed certainty that traffic density would justify the cost. Diesel was flexible, electric demanded confidence. But on the routes where that confidence existed, the results were undeniable. Acceleration improved instantly. Maintenance costs dropped. Energy efficiency soared. And for the first time, railways separated the act of moving trains from the act of generating power. That separation would change everything. The engine was no longer the heart of the locomotive. What if the real story was never about the engines at all? Steam thrived in a world with cheap labor, abundant fuel, and minimal coordination. Diesel thrived in a world that demanded efficiency, reliability, and flexibility. Electric thrives in a world built on dense networks, precise scheduling, and centralized energy management. Each locomotive matched its era. Each one solved the problem of its time. Railroads don't chase innovation, they chase survival. Electric locomotives represent the most efficient solution railways have ever deployed. Instant torque, minimal mechanical wear, zero onboard emissions, precision control. On busy corridors, nothing else comes close, but even electric has limits. If electric is today's answer, what could possibly replace it? That depends on energy, not locomotives. Electric trains are only as clean and sustainable as the power feeding them. The future now lies in grids, storage, renewables, and system-level optimization rather than engine design. The locomotive has stopped evolving alone. It now evolves as part of a network. Steam was about force. Diesel was about efficiency. Electric is about coordination. That is why steam did not slowly fade away. It was replaced. That is why diesel did not disappear overnight. It still serves where flexibility matters. And that is why electric dominates where scale and density demand it. These machines are not rivals. They are chapters. Steam built the railroads, but demanded constant sacrifice. Diesel made them practical, predictable, and global. Electric redefined what efficiency and performance could mean. So here's the real question. If electric trains represent the most efficient system we've ever built, what happens when their limits finally appear? Tell us what you think in the comments. And if you want more deep dives into the machines and decisions that quietly reshaped history, watch the next video on your screen and subscribe to the channel. Because progress doesn't arrive all at once. It arrives when the old answer finally stops working.